What's up, guys? My name is Peter. Welcome back to the Vertical Intelligence Insight Hub interviews. So today I'm with Matt. Do you want to introduce yourself?
Hi, yeah. I'm Matt. I'm currently a junior. I'm studying honors math and business, concentrating in stats and data science. And yeah,
Yeah, thank you for joining. Thank you for taking time out of your day and speaking with me.
yeah, for sure.
Yeah. So since this is all about we're trying to learn about AI and machine learning and stuff, right? What AI projects have you been working on recently?
Yeah, so right now I'm working on basically trying to solve this game. It's called Figgy. Um,
Yeah.
so basically I'm using a PPO, which is an algorithm, proximal policy optimization, in order to try to basically solve this game from a game theoretic standpoint. It's a real-time game has its own complications, but basically I'm recreating GTO for this like new game, right? And that's like a reinforcement learning problem. So I'm getting a bunch of these different models to play against each other in the environment that I coded, and hopefully it'll converge to something cool. Apart from that, I'm also trying to build a large interconnected computer, which is basically just being able to inference or train um, a singular model across different consumer grade devices, so like on personal computers rather than on GPUs in data centers, and being able to leverage the unused power of personal computing in order to develop really big models together.
I see. The game's name is called Figgy.
Yeah.
Figgy are like what is the game exactly? What are the rules? And are you playing against like live players, like other players who build their own models?
Yeah. So you can read the rules online, but it's basically a card game where you are trying to find so there's going to be one suit that has some value to it. Every other card has zero value. And you're trading these cards. You're basically buying and selling these cards with other opponents. Usually it's played with four or five people. You're buying or selling these cards from other people in order to try and just maximize your profit. So
I
it's a smaller simulation of high frequency trading in the real world.
got it. Okay. Yeah. Is there a reason why like using a machine learning model is better for that game versus just creating your own strategy?
Yeah, so obviously like this has been like an age-old question, I guess. Um, why don't you just like have an expert come in and then just do the same thing? And the reason is kind of that machine learning models are better able to understand the space a lot better because they're able to iterate through a lot more actual variations of a problem space, right? So for example, think about like chess or Go, right? Go is like the most famous one example, like way back when, right? Of a computer being able to iterate through a state much faster than a human would be able to, such that even if a human even if you have like a professional who would create a strategy, the strategy wouldn't be as refined as a model that's been able to see not the approximation of like a good strategy, but the true best strategy possible. Which is why nowadays most games humans are outperformed by AI, at least for ones
Right,
that
right.
have like AI built for them.
Got it. Yes. Since it is like in a constrained space, right? Like if we're in like an open world, then humans will do better. But because there's like a set of rules, that's what makes the iteratability. That's what allows the AI to learn because it can iterate so many times within the confines.
Yeah, yeah. And I would say that this constraint space is kind of like we're moving towards a world where you're able to iterate over things like the real world because the real world still does have constraints, and those constraints are just called physics instead of whatever your game rules are, right? And which is why we're able to see a lot of models be able to do things like predict the weather or self-driving cars is like the famous example. But you also have a bunch of different control systems with robotics that can be controlled by these systems better than humans can control them because the system that we see in the real world is constrained to some extent, and can be interpreted by a machine.
That's true. Yeah, that's true. Yeah, and for your computer project, so like just the idea that I got from
Mhm.
that is you have a bunch of like these decentralized GPUs, right? Which are from like from people's
Mhm.
personal MacBooks. So what you want to do is
Mhm.
want to connect all of these together into one like basically like big decentralized data center, and then train a huge like AI model based on that.
Yeah, yeah, yeah.
Yeah, I mean
That's
this
like the
like
gist of it. Yeah.
how like how are you doing it? What
Yeah.
are the frameworks that you are using?
Yeah. So models have been able to be sharded for a while now. So that's the term of like basically splitting up your model into a bunch of different smaller pieces. And when you actually pass information through a model, when you have a model run basically, when you pass information through, it is iterative. And you basically do step one, step two, step three, step four, whatever. And then so if you, these are known as like layers usually, and if you split off these layers into different machines, then you're able to have one machine process the first couple layers, pass it on to the next, onto the next, onto the next, until you actually have an output. And when you're updating, you just go the opposite direction. It's called backpropagation. But basically, because machine learning models nowadays, especially deep models, are so modular, you're able to actually leverage that fact and split all of these um, large, huge models up into a bunch of smaller pieces.
Got it. Yeah, yeah. But well, the thing is, like, if you got a million math books training this huge model all at once, like, dude, like,
Mhm.
do they still need to be connected to the cloud in some way? Like, because how are the different computers going to know that like what their task is?
Yeah, so that's just a syncing problem. All of these would be have to connect to a server that I'm making. And then basically it would just you would know like there is one centralized server that's basically controlling the whole operation. Like getting telling each computer where to send data to the next one, and what their next instructions are. Obviously, like for personal computers, this is a harder problem because nobody's going to keep their computer up all the time. And if someone just turns off their laptop, then we need something called fault tolerance because obviously that node just disappeared. We need some form of backup to make sure the entire system runs smoothly.
I see, I see. Does the main system need a lot of compute? Like it's obviously going to be far less than the compute in like data centers that are actually training. But I would assume like it would
I would
still
say
be quite big, you know?
I would say like nearly none because like all the main system has to do is send out the data and tell computers to send their output to somewhere else. It doesn't actually have to interpret that output at all, right? The main systems is just like basically a control center, right?
Mhm.
And they're telling one computer, hey, you did all this work. Now send this information to this computer for it to do all the work, right? The main system itself isn't actually doing all the matrix multiplication. It isn't actually processing anything or like too in depth.
Okay, I see. Yeah, what has been the biggest challenge like for you for this project?
I would say that largely the extremely different architectures and the um, support on these architectures um, for specifically machine learning. So, so obviously you have like NVIDIA. Ideally, an ideal if everyone's personal computer was like an NVIDIA GPU, then everything would run perfectly, right? But they're not, and all of these different types of GPUs, especially like Mac, MPS, or like Mac Metal, right? The software on top of that, NVIDIA MPS instead of CUDA, sucks, and it's not able to basically you fully utilize the GPU for what you want to use it for. And then also being able to transfer all of this information to another system and then get it onto their GPU and do all of that. And that's something I've had a little less experience with. So tackling that as a new issue is a lot more interesting. And combining that with like my previous knowledge of machine learning.
I see, I see. Yeah, how far along are you in this project? Because like I assume if you actually get it to work, like that'll be quite revolutionary.
Yeah, so I have like inferences done. So like I'm able to run models that my own computer can't like host by itself. So I've gone like a couple around like half a dozen machines, and then I was able to split one model llama onto all of them, and it was able to run inference. Obviously, there's a bunch of optimization to be done, but that's kind of where I'm at right now. And backpropagation was easy as well, mostly because I had a very closed system. But as that becomes more dynamic and larger, more issues will come up.
Nice, bro. Yeah, yeah. In the future, once you do get it to scale, right? Like in order to incentivize people to give like their compute to you for you to like use that compute to train, like you'll just give them like a local machine learning model for them to use, so like they don't have to pay for GPT or anything like that.
Yeah, basically. Especially since DeepSeek came out, this project came like much before then. But obviously, since DeepSeek is out now and it's open source, that would probably be like the easiest thing to offer, especially since so many countries are banning it, but it is open source. Um, there's a really easy way to just offer that to consumers. Say, hey, your information is not going straight to like the CCP or
Yeah,
something like that, or whatever concerns they have about like the online server. And then that I feel like is probably like a really good reason for people to give up something that they weren't using regardless, which is their processing power.
I see. Okay. Like, is there enough computer space to store the DeepSeek model? Because like the online videos I saw, like you would need multiple Mac
Hmm.
minis to get it to run on your local machine.
Yeah, yeah, yeah. Well, I mean, obviously, like you can't run it on one machine, but like the point is to have multiple machines.
You
That's the
got
entire
all
point of the
working
project,
together.
right?
Yeah.
Yeah, yeah, yeah. And then so you don't like you might need like a dozen computers to get DeepSeek to run like properly, right? But after you get those dozen computers, then like everyone has access to it, right? And like obviously you might need to scale a little bit up because the amount of inferences might increase, but like at its core, like it doesn't take that many computers to actually run large models.
Nice. Yeah. So this is kind of like a decentralized cloud service, right? For
Yeah,
training
basically.
ML models.
Yeah, yeah, yeah.
Yeah. Cool. Yeah. So have have you done any research in the deep learning field? And if you have, like, what was your experience?
Yeah, sure. So I've been doing research since freshman year. I was originally or I'm still in Professor Joe's lab at NYU. He's focusing largely on reinforcement learning, which is why I've done a lot of reinforcement learning. My first project was pretty cool. It was more an application one. I hadn't really known the theory yet because I was a freshman, but it was like applying a DDQN or a double deep Q learning network onto like data science articles for recommendation system. That got me really, really hooked. And then I started actually learning the theory. My freshman year summer, I did a bunch of like natural language processing stuff. Basically, I was trying to see if models could learn off of corrupt data labels, which is basically incorrect data. Obviously, the internet's full of noise, and when you scrape data off the internet, then a lot of your data is just going to be wrong or not helpful to the model. I wanted to see how resilient models could be and how we can make these models more resilient against noise in the data without actually having to manually label what data is noisy. And then this past summer, I was at Rice University, and I was working with Dr. Marini. I was working on basically these things called self-organizing maps. They're a pretty old type of architecture, but they're pretty cool. And then I was basically trying to see how you could create a loss function for them. They don't have a loss function like normal deep learning methods do. I was trying to see how I could create like basically an analog for a loss function that would allow me to have the same properties an SOM would have, self-organizing map would have, but be able to connect it to other forms of deep learning. And then so something cool I was able to make was like a CNN connected to an SOM, which hadn't really been done before. And then look at the results of that.
Jeez, man. Yeah. That's very interesting. Wait,
Mhm.
so you talked about the like DDBQM for reinforcement learning. Is that right?
Yeah, DDQM, yeah.
Yeah. what is that exactly? Like,
Yeah, double deep queue networks. So queue learning is the one of the more popular forms of reinforcement learning. Reinforcement learning being creating a model that is able to take it actions in an environment where queue learning is basically like you have this giant table, given any state, I want to maximize my basically reward, right? And then so the model is able to learn off of that. Um, it's a deep. The first D is or one of the D's is deep, which basically means instead of having that table, we're going to replace that with a neural network, which is able to approximate the table and generalize a little bit more. And then the other one is double, which is basically when you have the original queue network, it tends to overestimate the reward for especially for things that it hasn't explored because you want to incentivize exploration. So basically what double does is there's a cool paper on it, but basically gives you two estimates, like one that's like the normal estimate, which is generally an overestimate, and another one that's mathematically usually an underestimate. And then obviously if you have those two, then you can have a better estimate of the actual reward function, and then you're able to converge a lot more stably.
I see. Cool, cool. Got it. Yeah, like for for all of these research roles, like what was your role within the team? Like did you help them get the data? Did you help them code stuff or
Yeah. So it kind of depends. Obviously, like earlier on, I was more so like cleaning the data. Well, I mean, my first project was with like actually doing research was I could actually code the algorithm myself, right? I was tasked with actually implementing it,
okay.
which is pretty cool. And then so after I got through implementation, then I kind of got into like screwing around a little bit with like the parameters of the actual models themselves and like see what I could tweak to make things better. That's kind of what I was doing my freshman year summer at the University of Cambridge. And this past summer, it was just all math. So I was looking at the algorithms themselves and seeing what guarantees I can make of them, what rates of convert, or like basically like how many operations it takes, how does the operation scale? Is this actually better than not using them at all, like an SOM at all? Stuff like that.
I see, I see. Okay, yeah. When when you're doing research, like what is the role of the a professor? Like are they also using most of their time to analyze the math that goes into it?
Yeah, so it depends on how supportive your professor is. I've been lucky to have very, very supportive professors. Um, in general, if you're an undergraduate and you're doing research, then the professors will be a little bit more hands-on. They'll probably have a project that they want to do, and you'll be able to help them on the project, right? But if you're doing like an actual like research internship at a university, like an REU or a SURF or whatever they call it nowadays, then usually you go into those with your own ideas. And then you have like the agency of, you can control the direction that the actual project takes, and your professor is more like an advisor. This is more similar to like when you're actually doing research in like your PhD or anything like after graduation. This is kind of how you would usually work, where you're the one actually doing the research, and the professor is kind of there to help you. They might not know exactly what you're doing, but they can help you understand things in a broader sense, give you like resources, help you understand what you're doing a little bit better. And if you really need it, they'll join with you and like do the math.
Okay, got it, got it. Yeah, did you apply to these research opportunities or did you just reach out to them?
Yeah, so these research opportunities you apply to them. And then usually you try to see if you have a good research fit with a professor. And if you do, then that's always good.
I see. Cool, man. Yeah, yeah. Yeah, so we met through the BAC machine learning team. Like
Hmm.
yeah, well, like what was your experience with BAC in general and like teaching other people about machine learning?
Yeah, so I think that the BAC's machine learning team, BAC is a undergraduate club here. Um, it's probably like the best resource that undergraduates have for actually like learning machine learning stuff. I felt like there was a huge gap in actually being able to learn the algorithms behind machine learning. So like obviously like you have a bunch of courses and a bunch of like clubs that will teach you how to like import sklearn,
Right.
import TensorFlow, whatever, and then like you just like do model equals linear regression, and then you do model.fit, and then voila, you have your data science project for the semester or whatever. And then so I felt like all of that was kind of very surface level. So I was very interested in BAC machine learning team and being able to expand upon it because it was the only place where I found that actually lets you see, hey, you're importing these models. What do these models actually do? How do these models actually update? What are the assumptions they make? What are the things that are wrong with them? How do we improve upon them? And then so after I joined the machine learning team, I eventually became I eventually became co-director. And then I think it was a really, really great experience being able to go through all of the new stuff that's come out in recent years, and being able to get other people really, really hyped up about actually learning about machine learning itself as a science instead of as an application.
Right. Cool. Yeah. Uh, the team does like projects at the end, like towards the end, right? In the last couple weeks,
Hmm.
like what were your favorite projects that came out of these teams?
Yeah, yeah, yeah. There were a bunch of cool projects. Um,
I mean,
yeah, okay.
The Riz GBT was pretty good, man.
Yeah, 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 yeah. RISGPT was definitely up there. There was one team that basically took a bunch of like data, took a bunch of data from Tinder and then fine-tuned the model to basically have Riz and be able to swoon over all of the bots on Tinder. And then there was also another really cool one that basically tried to learn how to play poker. There was another one that was like automatically transcribing. I think that was yours, right?
Yeah, yeah,
Yeah, automatically like clipping podcasts, which was
yeah.
really cool.
Podcast, yeah, like you would
Um,
insert like a file and then a bunch of
yeah,
transcripts.
yeah, yeah. Yeah, so that was, I feel like all of these projects are like, you can just take machine learning into so many directions, especially when you actually understand it a little bit better. Obviously, like nowadays you hear like, oh, like th this is another startup that does, oh, LLMs, and it's just like a ChatGPT like 20.0, like it's all the same stuff, right? And being able to actually understand machine learning affords you the ability to do a bunch of these much cooler projects, in my opinion, on like in things like finance, in like video, in like text, in all of these different fields and games and stuff like that. Um, and that's like probably like the best part of the machine learning team being able to see all the projects then at the end.
Right, exactly. Yeah, yeah. Like like we talked about how machine learning is branching out from the more constrained spaces into like actually understanding the real world, right? So I feel
Yeah,
like now because of that, like there's so much more applications that it can be used for.
yeah, for sure.
Yeah. So so where do you see yourself in the next 5 years? Like what vertical of AI or like machine learning or like some other industry do you see yourself like working in, making an impact in?
Yeah, so let's say the largest. So ideally, I'd be doing my PhD. If I'm super ambitious, maybe I'm done 5 years, probably not. Um, and then so as for like the specific field, I think I'm really interested in like optimization and like online learning. I think like all of the math behind being able to converge to your solution very, very fast, like is kind of like the backbone of how machine learning learns. Um, and I feel like the math behind it is like really, really pretty. And then so hopefully I'll be able to specialize in that specifically. I'm also definitely interested in like reinforcement learning, which is kind of adjacent, and distributed inference and stuff like that. But those or like distributed inference especially is a little bit more computer science. I don't know if I exactly want to go down that route. But definitely, hopefully rather a PhD in like a machine learning field. hope like ideally that would be something along the lines of optimization.
Right. Sounds good. I mean, if you manage to build a big like cloud service computer, like you might be working on scaling that, or
Yeah, yeah,
or you might, get an exit already by then.
yeah.
Yeah.
Yeah, yeah. I feel like obviously there's a bunch of money in machine learning right now, but I think I like machine learning more for like the actual algorithms and stuff behind it. I think the math is really cool. And I would definitely be more interested in actually exploring the stuff behind that, rather than like I mean like I also wouldn't mind if like a VC firm gave
You
me
get a
$50
big
million
paycheck.
dollars. But yeah, but I think I'm definitely more passionate about the actual algorithms behind it.
I see, I see. Yeah. So for students who are like interested in AI machine learning, but like don't know exactly where to start, like what advice do you have for them?
Right. I would say start with the math. Um, okay, learn your first language, probably Python, and then go into the math. Um, I would say like if you don't know the math, it's kind of hard to understand anything. Obviously, like if you aren't interested in the actual algorithms themselves, you're just interested in AI and you're interested in how to use it, then the math isn't really necessary. You can probably take a data science course. There's a bunch of them online and like at most universities. Um, and there's a bunch of like these Kaggle competitions and notebooks online that will teach you exactly how to take data, clean data, put it into a model, see if the output makes sense, and then if you can do all of that, then you're in a great place to understand AI and do a lot of data science. If you are interested in the step beyond that, which is like research itself, of like the models that these data science people use, then definitely do the math. Learn the math first, and make sure you actually understand it. And because if without it your like future understanding, you're not gonna actually like be able to comprehend anything beyond that. Deep Learning is a great book, or like it's just called Deep Learning. It's
Deep
the
learning.
one published by MIT.
Who's the author?
Uh, I have it. Wait, let me find it.
Yeah, I can link it like in the blog of the website as well if people want to check it out. Yeah.
Sure. It's Yeah, Deep Learning by Ian Goodfellow, Joshua Bengio,
Yeah, yeah,
and
got it.
I butchered that, and Aaron Corville. But that's a really good place to start. Basically it's very comprehensive, in how all of that works.
Oh, it sounds good, man. I mean, I definitely agree with the math part because like when you're implementing, like if you want to build anything great, like I still think you need to think from first principles and like the math is first principles, right? So if you want to build anything like
Yeah,
genuinely complex, you have to first
yeah,
understand
yeah,
how the foundations work.
yeah, exactly. I don't know if you're trying to implement the newest algorithms yourself before anyone's like created a package for you to do it. You're never going to be able to get there if you don't understand
Right,
anything.
that's true.
Um, and then so if you want to be on the cutting edge, you have to do the dirty work first.
All right, man.
Yeah.
Okay, yeah. Thank you again for taking the time to come out here speak with me. Is there anything else you wanna
Yeah, it was
say?
great talking to you.
Yeah.
Um, I don't know if you're interested in machine learning, join the BAC machine learning team.
All right,
I'm
all
no
right.
longer heading
That's
it,
where
but the
NYU
people,
people. Right.
yeah, for NYU people. If you are interested in machine learning, it's the best place to be. I'm no longer heading it, but the people who are running it now are also really great, really, really smart and talented. Um, if you are interested in machine learning and you're not at NYU, just start, build something. I would say like there's so many resources online. The worst thing you can do is just say I'll do it tomorrow. So yeah,
Okay. All right. Thank you, man.
yeah, sure. See you.